Humanity has always dreamed of crossing the vast distances between Earth and the planets. In the early 1960s, NASA believed it had finally found the engine powerful enough to do it. Not a chemical rocket, not a shuttle, not an ion thruster. Something far more ambitious. A nuclear reactor, burning hotter than anything mankind had ever launched, pushing spacecraft toward Mars at speeds the world had never imagined. This was Project NERVA, the nuclear engine for rocket vehicle application. A forgotten program born from Cold War pressure, scientific optimism, and the belief that nuclear power was the key to conquering the solar system. Today it exists only in faded photographs, damaged test stands, and classified documents slowly turning yellow in archives. But in its time, NERVA was the future, and for a brief moment, NASA was ready to fly it. The story begins in the mid-1950s, when the United States was searching for ways to leap ahead of the Soviet Union. Chemical rockets were powerful, but they had limits. They produced huge thrust for a few minutes and then died. If the United States wanted missions to Mars, Venus, or a permanent human presence in deep space, it needed engines that could produce far more energy. Scientists at Los Alamos believed they had the answer: a compact nuclear reactor that heated hydrogen to extreme temperatures and expelled it through a nozzle at unbelievable speeds. In theory, this engine would be twice as efficient as any chemical rocket. It could burn for hours instead of minutes. It could carry spacecraft deeper into the solar system. And unlike traditional rockets that required enormous fuel tanks, a nuclear thermal engine needed only a small supply of hydrogen. The idea was revolutionary. NASA partnered with the Atomic Energy Commission, forming a massive research alliance. They started planning the first prototypes under a program called Rover. Later, the operational rockets became known as NERVA. At a remote desert test site in Nevada, engineers constructed huge concrete bunkers with thick steel doors. These weren't ordinary rocket facilities. They were designed to contain radioactive material in case something went wrong. The desert floor shook as the first nuclear reactors were lowered into test chambers. The experiments were dangerous. Every firing had to be carefully controlled. Engineers worked behind blast shields and remote cameras. Hydrogen gas flowed through channels inside the reactors, heating until it glowed, then blasting out of the exhaust bell at speeds no chemical engine could match. Each test produced a rumble that echoed through miles of empty desert. Despite the risks, the program advanced quickly. By 1964, NERVA produced its first major success. The NRA-2 engine remained stable under high temperatures, running long enough to prove that nuclear propulsion was not just possible, but practical. Engineers celebrated quietly. Classified documents from the era described the tests as encouraging, safe, and meeting performance goals. For once, nuclear technology seemed ready to be used for exploration instead of weapons. President Kennedy's call to reach the moon forced NASA to focus its budget on Apollo, but behind the scenes, the agency was already planning the next frontier. The long-term vision was clear: a nuclear-powered spacecraft that could carry astronauts to Mars in the 1970s. Documents from 1965 show blueprints for what NASA called the Mars Excursion Module, a spacecraft with a NERVA stage at its rear. The mission outline was ambitious. Astronauts would travel for months in deep space, land on Mars, explore its surface, and return within 2 years. The nuclear rocket wasn't just a dream, it was the foundation of NASA's post-Apollo future. In 1967, NERVA succeeded again. The NRX-A6 engine ran at full power for more than an hour. No chemical engine had ever maintained such heat and thrust for that long. Engineers were stunned. Test reports describe reactor temperatures exceeding 2,400 degrees Celsius. The fuel elements held together despite the heat. The nozzle remained stable. Even the radiation leakage stayed within the expected limits. The Atomic Energy Commission believed NERVA could be ready for flight within 10 years. NASA agreed. The agency incorporated nuclear propulsion into its official 1969 long-range plan. The plan listed a crewed Mars landing in 1981, a permanent lunar base, and a fleet of nuclear-powered cargo ships traveling between Earth orbit and Mars. For a moment, it felt inevitable. But technology isn't the only force shaping history. Politics, funding, and public opinion weigh just as heavily. And as NERVA advanced, the world outside the laboratory started changing. The Vietnam War drained the federal budget. Social movements demanded spending on education, health, and domestic programs. Public support for expensive space missions began to fade after the moon landing. The idea of launching nuclear reactors into orbit also terrified some politicians. They worried about accidents, contamination, and protests. Within NASA, the Apollo program itself became a heavy burden. Engineers who had once dreamed of the future now scrambled just to complete the remaining moon landings. Mars was slowly pushed aside, and NERVA, once a central pillar of exploration, lost political protection. The program faced its first major budget reduction in 1970. Congressional hearings questioned why NASA needed nuclear rockets when the space race had already been won. NASA officials tried to defend the program, arguing that chemical engines could never achieve interplanetary goals. But the mood in Washington had shifted. The excitement of Apollo 11 had faded. NASA was told to scale back. NERVA engineers continued working, but the pressure grew. They cut tests, postponed upgrades, and canceled the development of advanced high-temperature reactors. The program was still promising, but its momentum was slowing. In 1972, the nuclear engine achieved its final victory. The XE prime test demonstrated full thrust under simulated space conditions. The engine fired while suspended vertically, replicating how it would operate in flight. Performance exceeded expectations. Heat levels remained stable. Hydrogen flow remained perfect. And for the first time, engineers believed the engine was truly ready for space. But outside the test stand, the decision had already been made. President Nixon approved the space shuttle as NASA's next major program. The shuttle needed funding, and something had to be sacrificed. Nuclear propulsion became the target. The program was officially canceled on January 5, 1973. The engine that could have taken humanity to Mars was abandoned. After cancellation, the test sites were dismantled. Some reactors were sealed and stored. Others were buried beneath layers of concrete. A few engines were preserved in museums, their surfaces worn, their structures stained by heat. Images from the Nevada test range show long, empty trenches where exhaust once roared. The control rooms are still there, filled with analog dials and old wiring. The desert has reclaimed much of the facility, covering it in dust and silence. NERVA faded into history, but the legacy didn't disappear entirely. Many engineers believe the nuclear rocket was decades ahead of its time. The data from NERVA tests remain some of the most detailed propulsion records ever collected. Modern nuclear thermal engine studies still reference documents from the 1960s. Even today, NASA's proposed Mars missions often return to nuclear propulsion as a key technology. Rockets using chemical fuel require long travel times. Nuclear thermal engines could cut the journey almost in half. Discussions in recent years show design concepts remarkably similar to NERVA, using improved fuel elements but the same basic principles. In a way, the ghosts of the Nevada test stands still influence the future. The question remains, why didn't NERVA fly? The technology worked. The tests succeeded. The risks were manageable. Many historians argue the program wasn't canceled because it failed, but because it succeeded at the wrong time. The public wanted peace, not nuclear rockets. Congress wanted savings, not interplanetary adventures. NASA wanted the space shuttle, not a Mars ship. And the Cold War shifted from exploration to geopolitical maneuvering. The moment of possibility slipped away. Today, the surviving photographs of NERVA look like relics from another universe. Black and white images of reactor core assemblies, engineers in heavy protective suits, massive test stands rising from the desert, cranes lowering more than 30 tons of machinery into steel chambers. The world forgets how close we came. The nuclear rocket wasn't a fantasy. It was built, fired, tested, and proven. A generation of engineers believed it would open the path to other planets. They weren't wrong. They were simply too early. Project NERVA stands as one of the greatest what-ifs in the history of space exploration. A machine that could have transformed human destiny. A rocket powerful enough to bring Mars within reach decades sooner. A forgotten engine that carried the hopes of a future that never arrived. And in the quiet desert where the reactors once roared, the story waits for someone to tell it again.